And I would like to announce the first talk, which is about BCAL, the Bose-Einstein Condensate and Cold Atom Laboratory. And yes, Lisa, the stage is yours. Please.
Thank you very much, Maike. So this really now feels a bit like preaching to the choir, because all of you probably know what I'm going to talk about, and I'll take some swerves into a bit of basics on this. So I'm going to talk about BCAL today. BCAL is short for Bose-Einstein Condensate and Cold Atom Laboratory, which is a rather large collaboration from different institutions, including DLR and NASA, to bring an experiment to the International Space Station. And if you remember anything from this talk, what I want you to remember is the logo, because the logo already says it all. So of course there's the name on it, the short name and the long name on it. From the long name, you can already see that we are going to work both with condensates and with cold atoms, since we have different species on board. You can see the International Space Station orbiting Earth on it. So the idea is to bring this experiment to the International Space Station. You can see the word laboratory, so it's Bose-Einstein Condensate and Cold Atom Laboratory, which means two things, as a laboratory usually does. A laboratory is something which is not dedicated to one specific purpose, where we do one specific experiment, but a laboratory is usually something understood to be a multi-purpose, multi-use facility, meaning that there are different experiments to be conducted by different experimenters on this facility. And as I said before, this is a big collaboration, which is also made possible by a NASA DLR collaboration, with which we have access to the interesting and unique environment of the ISS, or the microgravity environment on the ISS more precisely. And on the other side, we do have DLR financing the payload and enabling us to actually have the money to build the payload itself. So the first thing that I would like to spend some time on it is, what do we mean by multi-purpose facility and how did we arrive there? And all of this started all this process started in a workshop in Bremen in 2017, where the community met and we discussed ideas of what would be nice to have in an experiment on the ISS. And there were a lot of ideas bounced around, and a lot of different people wanted a lot of different things. And so we had to somehow condense that down. And what was then instated was something that is a surrogate user. So those were people that were chosen from the scientific community to sort of boil down the different ideas and different scientific research areas into something that we could use as a baseline requirements document. These surrogate users were called the Science Definition Team, and reflecting the collaboration between NASA and DLR, or also the US and Germany, we had two different science definition teams, of which also Nathan is here, and he's going to talk about some CAL ideas later on. From there we went on, and basically there are two roads that we then had to take. The first one was, as I said, that this science definition team then formulated our science envelope requirements, the SERs, which are then to be found in the SERD in the document, which gives us a baseline to which we want to design. So this is really a sort of the Bible that stands above BCAL, from which we take what we need to do, what we need to achieve, and then actually flow that down into our design and into what we can do. And those are divided into 6 areas, and I'm going to come to them in a second. And on the other side of that, equally important is the surveillance and the review of realization. So the science definition team is involved in there, making sure that the surrogate ideas, or these ideas in the SERD, are actually realized in our design. But in addition, this is also accompanied by NASA, making sure that we actually adhere to all the requirements coming from the ISS and coming from going to space, coming from the launches. And this is, as for all space projects, or most space projects, divided into different milestones. The first one is a milestone, so the SCRR milestone, where we review the requirements. The second one is the preliminary design review, and this year there's going to be the critical design review. Between those, then there's going to be a little bit of a pause before we go into the flight readiness review just before launch, and then an operational readiness review once we are in orbit. So I would like to focus a little bit on these science ideas or these science envelope requirements that are the basis for BCAL. And there are 6 areas of those. So we the consortium that builds BCAL has a strong heritage in atom interferometry. So obviously this is one important part, including all these tests of the weak equivalence principle. But there are other areas such as the coherent atom optics, scalar Bose-Einstein gases, spinor Bose-Einstein gases, mixtures, strongly interacting gases and molecules, and also quantum information. And in all of these areas, different experiments are planned. And this is, Nathan, what I said before, where you are going to present these bubble formations that you saw in CAL, which we are also going to be able to produce in BCAL. If you want further insight into these different areas and want to read on them again for a second time, I would like to forward you to the science envelope requirements document or the paper which has been published by our consortium in the past. Can you still hear me? Hello? Because
yes, I can hear you.
Okay,
Yes.
yeah. All
Yeah.
the videos, one after the other, got lost, and I was just wondering whether my internet connection is going. Okay, perfect.
No,
moving on.
all good.
So another way of taking a look at these ideas would be the EPJ on quantum technologies, which has been published by the consortium in this year. So if you want to have further knowledge, further insight into those, where all of BCAL is described, take a look at either of these documents. And with that, I'm going to come to a little bit of an explanation. So basically, the basis for all of this is the Bose-Einstein condensate, and I'm just going to go very quickly through that. So the idea here is that we all know different states of matter where temperature is basically described by motion, meaning that in high temperatures, and the motion of the particles is high, leading to gaseous or plasma states. And then if the motion is cooled or the temperature is cooled, this motion also is reduced, leading to a condensation, in this case, from gas to liquid to a solid state. And also we all know that these particles can then be described by individual wave packets as per the de Broglie wavelength developed in the beginning of the 20th century. And now the idea is that if we continue to even further cool the substance from here on in, and especially considering bosons, for fermions, of course, the situation is slightly different. If we move on cooling the state from here on in, what happens what occurs is this so-called Bose-Einstein condensation. And as opposed to describing all of these particles by individual wave packets, now there's one wave packet to be described, one wave to describe the entire ensemble, giving us a very, very unique state. Now talk is cheap, and so I've included you here a picture where you can see the actual transition from a paper from last year, where you can see the actual transition occurring at a critical temperature of 130 nanokelvins, where then the Bose-Einstein condensation occurs. And so you can see that this looks very, very similar to what is in BCAL's logo. And so I just want to make sure that whenever you think about BCAL, whenever you see the logo, you know what's going on and what we are actually doing. And you can see a picture of sort of different condensates in here. Of course, it is displayed in a bit of a fashion that it looks as if it's a condensation, but the well-versed user will know that this is different experiments from Qantas, which are displayed in the logo. However, as a basis for BCal, all of this Bose-Einstein condensation, of course, also occurs in the logo. So whenever you think about BCal, you look at the logo and you will always know what is going on and what our plan is. Okay. So what is gained is that there are massive particles which can be described by one very well-defined wave function, which allows us to probe or sense certain fields, especially gravitational fields, which allows fundamental science. So we can do all these kind of UFF tests. We can do all these different areas displayed here on my slide. And we can also, in the microgravity environment, easier study complex phenomena easier, since all these gravitational counteracting forces do not have to be in place. So we do not have to have additional fields holding the particles in place, but the particles can evolve quite freely, and we can therefore study more complex phenomena and are more sensitive to manipulations of the particles, and can use smaller fields to manipulate particles as opposed to having disturbances due to additional fields that we need to counteract gravity on Earth. So one of the biggest challenges really in that is to go from the usual atom optic experiment, to actually mount that to the ISS. And as I said before, there come a lot of advantages with going to the ISS, or to microgravity in general. The observation time is longer, so the particles do not fall out of the potential, do not fall out of the active area, out of the chamber. There is no additional fields needed to counteract gravity, meaning that we can have smaller effect studies and more precise experiments, and also enable different scientific studies as opposed to what would be feasible on Earth. However, this challenge is quite large. So taking a whole laboratory and installing that to the ISS is quite a big challenge. And in that, fortunately enough, we do not have to do all of that on our own. But there was quite a lot of previous experiments going into that direction. And I want to mention a couple of experiments, a couple of examples here. One being the ICE experiments, which are done in Bordeaux on board of a plane. So they already had brought in a lot of experience. Then, of course, the Marius campaign, building that to a sounding rocket, and the really successful Qantas and Primus collaborations, which made that feasible first in the drop tower, and which is really part of our heritage for BCal. In addition to that, there are fountain towers. I have pointed here to the Very Large Baseline Atom Interferometer in Hanover. There are, of course, different fountain towers all over the world, which also allow to study these effects while the particles are falling within the gravitational field on Earth. As of recent, there's another experiment that also makes use of this microgravity environment, which is the American CALD, the Cold Atom Laboratory by NASA, which is of course also pointing us towards a way on how to actually do these things in microgravity, and how to be able to put these systems in orbit. And so basically my next slide is a summary of those. So there is a lot of heritage to BCal. There is NASA's Cold Atom Laboratory. There are the Marius 1, 2, and 3 missions, especially Marius 1, which is a sounding rocket mission, which created the first BC in space. The Qantas Consortium, which had drop tower campaigns since 2004. And then, since BCal can do more than those experiments, there's of course individual subsystems which had drop tower or satellite missions. And then there is additional laboratory experiments where we studied certain manipulation fields in order to enable us to actually go there, or to actually perform the experiments set for us in the science envelope requirements document. And so this is really what we came up with. In the end, this is the heart of BCAL. This is what we call the physics package. The center of it all is the atom chip in the vacuum chamber, with a certain amount of field surrounding it. We are going to study rubidium, or we are going to have on board rubidium and potassium, and both in fermionic and bosonic versions of these isotopes. Isotopes is the correct word here. And in addition to that, there are, so these are the basically the ideas that we have. There is the condensed atoms for the rubidium-87 and the potassium-41, and then we also allow for dual species experiments, especially for the universality of free fall tests, again from rubidium and potassium BCs, but also trapping of rubidium-85 and potassium-39 and potassium-40. And in addition, and you can already see that from the picture that I've shown here, there is a manifold of different traps and optical manipulation fields available. Of course, as I said, there's the atom chip in the center trapping as our main way of trapping. Then there are blue and red detuned optical traps, optical dipole traps. We will have magnetic field for Feshbach resonances up to 175 Gauss, additional radio frequency and microwave fields, and so on, all surrounding the center of the vacuum chamber, all surrounding the atoms, for enabling us to actually do all of these different experiments. So if we take that, then of course this physics package in and of itself doesn't function, so we need to insert that into what we call the physics package locker, which you can see down here. It's a bit tricky to see. You can see the chamber with all the field generation surrounding it in a magnetic shield, shielding it from the outside, and then being surrounded by a vacuum system, and all of that then being surrounded by a aluminum housing to actually insert it into the ISS. Now, yes, so in order to insert it into the ISS, we actually put it into what is called an express rack. An express rack is how these racks on the ISS or in the American module of the ISS are built in, so that we can insert that into these sort of cupboard structures, which are already on the ISS, ready for us to be used. And you can see the physics package, which is down here, and you can immediately see that BCAL does not only have the physics package, but also different systems. This is a block diagram where you can see the physics package on the lower side with the ultra high vacuum chamber, the coils and fields, so all of these manipulation fields surrounding it, and of course the detection and cooling optics. But then we also do have a laser system with optical preparations and a control electronics to it. And those are, of course, also taken on board and are included into our system. You can see them here with the electronics being in the smaller locker on the top and the laser system being in the other locker on the bottom. And then we take all of that and actually shoot it to the ISS in order to, and I've said that before, in order to enable us or enable people to study these different kinds of scientific areas. And in order to get there, we will then also have to go through making sure that this, through this surveillance process, making sure that BCAL is compliant both to the requirements and also to the ISS environment. So as a reminder, again, this is really the heart, the basis of it all, where we come down to. And from these different areas, what we can do, and from this challenge of actually including this whole laboratory into our system, into a system that can house on the ISS, BCAL can also be seen as a pathfinder. And with that, it is a pathfinder for both for applications on Earth. If we can do this miniaturization, this can help us develop applications for Earth, where we can do additional studies on Earth, but also for future satellite missions focusing on individual aspects, or again, a more of a laboratory environment for cold and condensed atoms. Let's see where we go. So where are we now? The next crucial step for us is the critical design review, which is going to take place this year, November. And then there's going to take some time, which is not what it looks like in this graph, until we deliver it to NASA to be launched to the ISS. The system will then be operated in orbit for a minimum of 1,500 hours and with a planned overall duration of 3 years in orbit. We will have all of the operation and surveillance going on, with then finally the data distribution and analysis. And if you are interested in performing any experiments on this very unique apparatus in this very unique environment, this is really what we are here for. This is really what the system is built to. And I would like you to reach out or start by reading one of the papers that I've shown you, making sure that, or seeing if your experiment would be able to be housed by BCAL on the ISS. And with that, I come back to my very first slide, making sure that this is the take-home message. Just take a look at the logo, which says it all, where we have the cold and condensed atoms in the microgravity environment on the International Space Station, which is a laboratory for multi-purpose, multi-user, for multi-purpose facility, or it's a multi-user, multi-purpose facility, and a big NASA DLR collaboration. And with that, I would like to thank all of my collaborators on which behalf I'm talking today, and also you for your attention. Thank you.
Yeah, thank you very much, Lisa. Hello?
Yeah, hi. Yeah.
Okay. It's always a pleasure hearing you talk about BCAL. For me, it's always a very interesting topic, because I'm not too much into all of this, technical stuff seen from the technical side. So always interesting. I would like the audience, are there any questions? From the most side, maybe not. I'm because you're all well known with that, but maybe there are still some questions. Yes, please.
I have one question. You mentioned the data distribution in one of your slides. At which time do you intend to distribute the data? Some time after the launch, or?
So the idea with this data distribution that I mentioned there is really the experimental data. So if the process would be that if you would be interested, you would then write together with our team a sequence that is then executed on board, and we're then talking about the data that is generated during that execution on board for your specific experiment. And that would then be distributed, we are still debating that, surely through a NASA system where they make it available publicly. And I would assume that that takes a couple of weeks, depending on the download capabilities that we have after the experiment has been performed.
So the process will be provided by NASA?
For now, this is definitely planned. We are currently in talks with DLR to see if DLR itself also has the capability of having like this publicly available storage capacities, which you could then like a cloud server with more security to it, obviously, but where you could then have a password and access that and download the data, which is yours. Similar to what ESA does in their experiments, and also similar to what ESA does, we will have to make those publicly available, because in the end, this experiment is publicly funded. So all of those will be made available to the PI developing the sequence, but then after, say, a year or two, I'm not sure how long we said that the data is going to be proprietary. You can have access even to data that was not yours. So there will be a server where these data can be accessed.
Thank you.
Yes, okay. Are there more questions? Just turn on your micro if you have one. Okay, then maybe I could ask something which is maybe a little bit more, yeah, from my side, it is something which is, I just want to hear your opinion on that.
Right.
What do you think is the most challenging part in setting up the whole thing?
BCAL in and of itself is very, very challenging. The thing is that I trust the teams that are working on it to be able to actually do the science and the physics. So if we would have unlimited space and unlimited mass, I don't think that there would be any issues. So it's really the miniaturization of getting all of this laboratory equipment that we would usually have unlimited room for and unlimited mass for into this very confined space. That is really the big challenge, developing all of that, making sure that it works, and making sure that even by miniaturizing and by developing the smaller systems, this more efficient system, making sure that it still works in the way that it was intended by the science definition team. This I think is the big challenge for BCAL.
Mm-hmm. Okay, thank you. More stuff to ask for. Okay, doesn't seem to be the case. So we are very well in time, I think. Yes, thank you again, Lisa, for this nice talk.
Thank you very much.
Yeah, it's always interesting for me to hear that. And I don't know, I think, yeah, I think we could start maybe with the next presentation already, because it's nearly 10 o'clock. So yes, maybe Manuel, you could start to share your screen. Oh yes, nice. And yeah, I would like to announce the next speaker, which is Manuel Rodriguez from ONERA. And he's going to talk about, yeah, I think an update about the microscope arrow data analysis for the test of the weak equivalence principle in space. Okay, then please, Manuel, go ahead.
Okay, thank you, Michael. Thank you to the organizers to invite me to this conference. So I would like to talk to you today about microscope on the space mission dedicated to the test of the equivalence principle in space. And I will focus on the error data analysis in this presentation. So after a quick overview of this space mission, I will present you the data science on the first published results, and I will follow with the data process. Some of the data process I will summarize some critical items, items we had to face in this long time of processing. And a special mention to some results of the systematic error analysis, which was one of the main points to solve in this mission. So maybe you know already this mission. So the microscope is French space mission dedicated to the test of the equivalence principle, which was performed on a microsatellite developed by the French Space Agency, ICRANet, and on which some contributors from ZAM also. We had some contributions from ZAM for a long time on this mission. I have to mention also that the co-PI of this mission is Hans-Jörg Dietus from DLR, and we have a long cooperation on this project with the ZAM team, and in particular Klaus and Michael, which is present today. The objective of this mission was to test the equivalence principle to 10⁻15, meaning that we like to compare the acceleration of the two bodies in freefall around the Earth. So in this specific configuration, as you can see in this picture, we have two cylinders orbiting around the Earth. And in inertial pointing, as you can see, the Earth's gravity is along the axis of the cylinder twice per orbit. But if the two bodies, the two test masses or the masses of the inertial sensor, then the measurement of the difference of acceleration of the two bodies will have the same profile of the gravity field if we have a potential violation. So the difference of acceleration is non-null if the violation is here. So we would like to compare two types of materials, so an alloy of platinum, platinum rhodium, and an alloy of titanium. The test masses are controlled by electrostatic forces. That's why we can maintain this configuration for a long time during several orbits in this mission. So the satellite is a small satellite of 300 kilojoules, more or less, and a little bit more than 1 meter cube. One particularity is also that this satellite is composed contains a system of cold gas propulsion for the trajectory and attitude control. But I will present it in the following slides. So the payload is a double accelerometer made of two test masses, one in platinum for the inner test masses, and the outer is platinum or titanium, depending on the sensor. So we have two sensors on board this mission. One we call the SUEP for the equivalence critical test with different materials, but we have also a reference sensor that helps us to verify all the data process and to check if the mission is going well. So we don't expect any violation, of course, with this sensor because we have the same material, but we expect a null value of the experiment. So it's a kind of reference sensor to verify that we measure any systematic on this mission. So each sensor unit, so each double accelerometer is linked to front-end electronics. So front-end electronics contains all the capacitive sensing that measure the position of the test masses, and which send this information to the interface control unit, which is the digital controller that computes the necessary voltage to apply to the electrodes to control the test masses. So this interface control unit gives back the information to the front-end electronics that converts this information to analog voltages to be applied on the electrodes. So with this kind of system, we can measure very accurate acceleration of test masses. So you have here the dimension. So typical dimension is about 100 millimeters for the sensor core of this accelerometer. So this payload is integrated at the core of the satellite. So this white cubic satellite. So you can see here the payload. So the sensor units on the front-end electronics that are integrated in this payload case. The digital electronics is placed on the wall of the you can see on the wall of the satellite. So you have here the reservoirs, the gas clusters, and we for this satellite we have a different mode of operation. For the initial pointing, as I've already said, that was only used for calibration, as you will see in the following slide. And for the science, so the EP test, we performed two rotation the satellite. So we rotate the satellite on the opposite direction of the orbit. So with a rotation normal to the orbit. So with this kind of rotation, we increase the modulation frequency of the projection of the gravity field along the sensitive axis. So the sensitive axis in this picture, you can see here, is along this axis, for instance. And if we rotate about this axis, the apparent variation of the gravity field along this axis is increased. So we have a frequency of the test, two frequencies for the test, one near 10 to minus 3 Hz, and the second one about 3 times 10 to minus 3 Hz. So the payload is inside a thermal cocoon in order to have a very slow variations of temperature inside the payload, and we will see that is one of the main points of this mission. So the satellite is a track-free satellite laboratory. With the propulsion system, we can control the angular motion on the linear motion of the satellite. So the idea is with this loop in the satellite, so we have the measurements of the accelerometer that provide 6 axis measurements, so the 3 linear acceleration and the 3 angular acceleration. The linear acceleration is used by the track-free controller to apply the necessary thrust to compensate any external acceleration applied to the satellite in order to modify the output of the accelerometer. And the angular acceleration is also taken into account with a kind of filter, hybridization filter with the attitude measurement. So we combine the two measurements to have a very fine attitude control. And we can also, in this way, have a very quiet environment for the measurement of the different principles. So you have here some samples of an example of what we have performed with the track-free controller. So with this system, so we have demonstrated that we can control to less than 3 times 10 to minus 13 meters per second square for the acceleration. And for the angular motion, you can see that we have a very small motion on the once integrated. We have micro radiant stability about the frequency. In this satellite, we have also some capabilities of generating acceleration. So we can bias either the star sensor or either the accelerometer in order to produce angular or linear motion of the star, the control angular or linear motion. So in this way, we can calibrate some parameters of the instrument by only biasing the output of the sensor. And we can also and we have some temperature thermal features on board each plate of the payload that allows us to generate some thermic stimuli on board in order to estimate the acceleration sensitivity to the temperature at different stages. So the science data was collected from more than 2 years, from April 2016 to October 18. So in October 18, we released a deorbiting system. So it's 2 wings. You can see in this picture 2 wings that were deployed. And in this movie, you can see on the right an optical view of the satellite taken by the Observatoire d'Azur telescope on the particular technique developed in ONERA which was developed for the detection of planets around stars in the space. So with this kind of technique that compensates the fluctuation of the air on the fluctuation on the effects of the light when coming to telescope. We can also use this kind of techniques to see satellites. So it was performed 2 years ago by a telescope in south of France. So it demonstrates that the twins were well deployed in order to deorbit the satellite in less than 25 years. So this mission provides a certain number of data, but for the science side, we can use only 20% of this time because most of the time was dedicated was non-usable for science. For instance, we have 23% of the time with eclipse. So that means that the thermal stability of the satellite is not guaranteed. So we cannot perform science. We can perform some technological tests, but not science. And we can see that a small portion of the time were dedicated to science and calibration. And we have also performed some tests to test the thermal behavior of the satellite, as I will present. So this was one main point also to check that the sensitivity of the instrument was well known for this mission. So the science session were composed of 2 types of sessions: the calibration, which were more or less 5 or 10 orbits, and the EP tests were performed with a duration of 20 to 120 orbits. So the total of the science is about more than 2,700 orbits. So quite small with respect to the total. So maybe, as you know, we have already published 4 years ago or 2 years ago a first result, which was based on only one session, so about let's say 7% of the available data today of the science data. So we have two publications on the sorcerers for these 2 sessions, one for the SUP, one for the SURF. So in this publication, we demonstrate that we don't have any violation at the level of 2 times 10 to minus 14. And this accuracy was led by statistical error. So the result of the statistical error from the mean square fit of the data to the gravity fit. So when we perform the fit, we extract the parameter and also an error. And to this error, we have evaluate also potential systematic errors that can bias this result. And this systematic error was dominated by temperature variations, the effect of the temperature variations on the accelerometer. And this systematic error was dominated by the fact that we don't know, in fact, the real temperature variation at this frequency, because we were under the noise, so we measure only the noise. So we overbounded this systematic effect by an upper value. And one of the objectives of the data process of the overall science data, so the rest of the 93% of the data was to better evaluate the systematic effect in order to reduce this point. And we have the same for the SLI. So you can see that both instruments measure a new value consistent with the error. So the final process is based on the measurement equation. So to be simple, if in any real world we measure the difference of the acceleration of the two test masses. So, but this difference is linked to if we had no defects at all, we measure directly the gravity field multiplied by this parameter. But in the real world, we have to cope with some defects. In particular, the accelerometer measures an acceleration, but we have two test masses, and the two test masses that doesn't measure exactly the same acceleration. We have the scale factor that must be equal to 1, but with a small difference to 1. So we have a small difference of scale factor that generates a disturbing term here. So we measure the difference of the scale factor multiplied by the applied acceleration. So this term of factor 2 is missing. And we have also other effects, the misalignment of the two test masses. So we have also misalignment parameters that will project the transverse acceleration on the axis of measurement. And we have also some miscentering of centering of the two test masses. The two test masses can be not well centered by construction because the mechanical accuracy is limited also. And this off-centering generates a signal from the gravity gradient. So the T is stands here for the gravity gradient tensor along all the axes. And we have also angular motion effects. So the matrix En is the combination of angular acceleration on the centrifugal acceleration that is seen in the differential acceleration because of this miscentering. And of course, we have angular coupling, noise, and so on. And what we would like to we have also offsets on systematic. So in this equation of measure, we can see that the parameter we want to measure, it can be hidden by other parameters. Okay. And some of these parameters, miscentering and the scale factor matching on this element, can be, in fact, calibrated. Is what we perform in flight. So we have dedicated sessions to estimate the F-centering on the misalignment on the scale factor matching. So the matching of the parameters of the two test masses can be performed by just applying the bias in the measurements of the acceleration on the satellite will be excited at a certain frequency along the S3 axis, and we can measure. So we amplify the command mode to see a difference. And we can also measure the F-centering by measuring the effect of the gravity gradient at 2 times the EP frequency, because in fact the gravity gradient have a strong signal, very strong signal at 2 times the EP frequency that can be used as a reference signal to estimate the F-centering. And because also we know very well the Earth's gravity gradient with the previous mission that we saw Goldship. The angular motion is estimated by the measurement of the star sensor, which delivers that can help us to estimate the angular velocity, angular acceleration. But in the finite process, once we have calibrated the data, we have seen that we can have some single events that can disturb the measurement or the process. And the first disturbing event is debris impact, meteorite or impact that are strong enough to disturb the measurement during a few minutes. So you can see that for about 1 minute, we have a disturbing signal that is lasting too long time. So we have to cut this measurement. So we eliminate this data. In the process, our process is not our process has to keep only even number of orbital periods of data. So when we cut the data, we have to lose more than the few minutes that are impacted by this debris. We have to cut about 1 or 2 orbits because we have to preserve this rule to keep even number of orbital periods, to be also not sensitive to potential signal that could be at combination frequency of the orbital frequency of the spin frequency of the satellite. And we have chosen also the spin satellite frequency as a half integer of the orbital frequency. So it's 9 here, in fact, 9/2 for the first spin, on the 37/2 for the second spin frequency. In this way, we can have a strong decorrelation from harmonics of the orbital frequency of spin frequency when we cut this segment like that. The second event that can disturb us is we have seen that in particular on the SURF, not in SUAP, in fact. On the SURF, we have sometimes some bias jumps, as you can see here, when we filter the data. So the blue is the raw data, so it's quite hard to see something except some transient here, very short transient here, because on this transient reveals in fact that we had a discontinuity in the measurement. So this is the response of the servo loop of the instrument that shows that has to cope with bias jump. And when we filter the data, we can see that at very small level, so at nanometer per second square level, we have a small jump. And this jump is not good for the data process because it could bias the evaluation of the parameter. So we have to cut also the session in small segments. So yeah, we cut it in 2 segments. This particular session. So we have a segment of 46 orbits on the second segment of 34 orbits. And we process the data of the 2 segments independently in this session. And the last disturbing effect is the satellite tracking that induce some glitches on the measurement data. So we can see here a time series of the acceleration. If we zoom, we have to zoom a lot. In fact, yeah, so you can see the scale here is 100,000 seconds. And if we zoom at the level of several tenths of seconds, you can see here a small peak that is due to the satellite tracking. And we have a lot of satellite tracking. And this particular tracking has the bad idea to be at the same period of the EP frequency. So if we don't do anything, we can see a signal at EP frequency that is due to this cracking and not to a potential variation signal. And what we have performed is we try to eliminate this particular glitch. So we have a process to detect this glitch. So we detect all the peaks above 4 sigma, 4.5 sigma, about the 3 axis, because the cracking is about all axes. And sometimes we don't see anything on X, but we can see something on Y. That means means that we can have something on it, but below the noise. So detecting above the 3 axes helps to detect it on X, the measurement axis, even very low tracking. And we eliminate the data. So we mask the data with 0. So we replace the data by 0, 5 seconds before the event, and 5 seconds or 10 seconds after the event. And when once the data is masked, we apply the iterative method that estimates and reconstruct the missing data. So you can see on this publication the description of this technique. This technique, to summarize very quickly, it's an iterative method that reconstructs the noise. So we estimate the best data that minimize the reconstruction, the error of reconstruction of the noise. And in this way, we can replace the 0 by something that is the best estimation of the data. And we, of course, when we eliminate some data, the risk is to eliminate also some information. So we perform also some tests so we add on this measurement an artificial signal at EP frequency, so false equivariation signal at different amplitudes, even at amplitudes below at the limit of the noise. And as we know this signal, after this process, we can recover the signal with 99% accuracy. So applying this process that can eliminate 10 to 20% of the data doesn't impact the EP signal. It was quite hard to put in place, but we have demonstrated this very nice result. So the techniques is described in this physical review physical paper, and we have also 2 other papers to be in preparation that will also describe these techniques. And the last point is the systematic error, which was dominated by thermal variations on the first publications. And what we perform is with dedicated thermal sessions on board. So we perform some thermal variation on the wall of the satellite, on the radiator of the satellite, inside the payload. And with all these thermal variations, we demonstrate that the process of thermal variation or thermal disturbance comes from the Earth albedo that enlight the FEU radiator and transmit by conduction a small variation of temperature at EP frequency on the FEU and after on the HU. So we, with these experiments, we evaluate all the filtering process, and in particular I would say the transfer function of the thermal variation, so between the FUE and the SU, or between the radiator and the FUE. And with this thermal model verified on board, we have demonstrated that the temperature inside the core of the instrument, which was the main topic for the systematic error, was below 0.1 microkelvin. So we improved by 2 orders of magnitude by the knowledge of the temperature variation. And this new knowledge of temperature variation leads to systematic error evaluation for the acceleration of 9, 10, minus 15, which can translate in a those parameter. So you have to divide it by 8 because the value of G is 8 meters per second square at this altitude. Also, we reduce the systematic error due to thermal variation by a factor 7. So in conclusion, the science data process is finished today. And we are now in the process of writing the final papers. So the work today is to prepare a special edition of the on microscope on classical quantum gravity. So we have a collection of papers. This edition will contain 10 papers. And some of these papers are already available on ArcGIS because they have been, most of them have been accepted, in fact. So you have here the references for some of the papers. And there are still some remaining, and in particular, the one dealing with the systematic errors on the Fernald results. And we hope to submit these papers before end of July. They are under internal review before submission. And the release of objective is to have the all papers accepted by end of this year. And I cannot finish this presentation before without having a special tribute to my friend Pierre Tougoul, the prime investigator of the microscopic mission, who passed away this year. So that's the end. And I thank you for your attention.
Yeah, thank you very much for this, quite full of information talk. And the last slide makes me a bit sad as well. So yeah, I'm a little bit
sorry for this.
But no, it's okay. He should be mentioned, of course, in context with microscope, because I think it was, in some way, it was his idea to go on with this, to start with this project, and to he pushed it forward over such a long time. And the microscope team knows how many valleys we had all over the time. Yes. Yeah, so thank you very much for this talk. Are there questions from the audience? Maybe something you are interested in to know? Just turn on your microphone and ask if you have a question.
Yes, hello, thanks. Great talk. I have a question regarding differential spacecraft potentials, because you are actually moving still in a quite low orbit. I would expect that you observe some space charging effects or differential charging effects on the satellite. Did you observe anything like this, and did it influence the measurements?
No, in fact, the altitude is about 700 kilometers. We are not, I don't know if we are very sensitive to charge at this altitude, but nevertheless, the effect of the charge will generate a kind of Lorentz force on the satellite. But as we are, as the satellite is a drag-free satellite, we compensate all the external forces. So even with disturbing acceleration due to charge, surface charge on the satellite, it will be compensated by the propulsion. But as far as I remember, I don't remember any topic related to charge. Sometimes we had some single events due to particles that comes into some on the star sensor, for instance, or on the onboard computer. We have some to reset the onboard computer, but it's something quite regular for satellites, but not for any disruptive effect due to charge.
Thanks.
Okay.
Okay, I think Klaus turned on his microphone as well.
That's a short question. So you have here the science unit and the reference unit are both parallel. This makes sense, of course. Yeah. But would it be good to have another unit which is turned by 90 or 60 degrees to have another reference or additional signal with related to a different direction?
You mean on this mission or for a future mission?
For a future mission. This mission is already gone, of course.
No, because in fact, we on microscope, we have also, in fact, we could theoretically also use the transverse information of acceleration on this mission, because we have performed the measurement along X. We may perform the measurement along X, but we could also perform the measurement along Z, which is on the orbital plane. This was not performed today. We have tried sometimes at the moment to just to check, but in fact, to really use this information, we have to use some existing calibration sessions to evaluate the scale factor along this axis, but it can be possible. It's something we could do in the future and use the transverse information to compare with the one provided by X. But in your question, you ask about having a reference sensor orthogonal. We don't think about that. What we thought about is to have in the next generation of accelerometer to have three test masses, three concentric test masses, and with improved. So the reference sensor will be concentric to the one performing the EP test, so we can perform the reference on the EP, the reference measurements at the same time as the test, so better than in microscope. And we thought also to improve the transverse accelerometer, so also have more dedicated session to well calibrated the transverse acceleration to have I would say a two-axis accelerometer that can help also for the to improve the test.
Okay, I hope that answers Klaus' question. Yes, and I think we are a little bit running now. We have to run a little bit. No, going to the next speaker. Thank you again, Manuel. Thanks. Good to see you again. So I'm really happy to have you in this meeting. And I would like to hand over to my co-host, Hauke, for going on.
Yeah, hi. Yeah, it's my pleasure to announce our next speaker, who is Nathan Lundblad, who hails from North America, from Maine, I think. And so it's the middle of the night for him. I guess that's why the slide is so dark. So yeah, we're gonna hear about a fascinating topic on fundamental physics. So ultra-Galt bubbles in space, especially on board the International Space Station within the CAL project. And so, yeah, please go ahead. The stage is yours, Nathan.
Thank you, and thank you for inviting me. Can you hear me all right?
Yes.
Yeah, perfect.
All good.
Great, thank you. So today I wanted to tell everyone about some experiments that we've been running on the space station recently through the CAL project. But first I want to motivate more broadly about why we're doing this. So if we look at the last couple decades of ultra cold atomic physics and how that connects to fundamental physics, it's really structured by the consequences of how we can vary temperature, geometry, dimensionality, topology, interaction in these systems. Think of these as all knobs that we can play in the quantum gas world. And whenever we can explore new realms in these 5 areas, typically really interesting new regimes have been uncovered. So can we envision, looking at this picture of the space station here, can we envision new homes for quantum systems that allow us to ask new questions in this area? Can we explore new regimes of temperature? Can we explore new regimes of geometry, et cetera, et cetera? And that's what we're trying to do in the perpetual free fall environment of the space station, is to take the quantum gas research world, that's been well developed on Earth, and put it in a new home. So today I want to explore this in a little more depth. So to introduce the NASA Cal apparatus, of which I am a user. I did not build it, and I did not design it, but I'm one of the users of the machine. And to talk about how we make these ultra cold bubbles, or these shell structures, with the Cold Atom Lab, and actually also present some of the Cal Run 1 observations that we're currently in the process of analyzing and writing up. So our work with Cal is focused on taking established Bose-Einstein condensate techniques from the Earth and use them in perpetual freefall and microgravity to make a bubble geometry Bose-Einstein condensate. In the literature, you can find this sort of discussed as, in theory, as BEC on the surface of a sphere or an ellipsoid, or superfluid films on curved surfaces, things like that. The physics open questions here really seem to coalesce around the behavior of many body systems on these curved surfaces. So how do vortices behave on curved surfaces? How do the effects of these topological, some call them hedgehog combing theorems, work when you have vortex systems on curved surfaces? Is there a possibility of a 3D to 2D crossover effect, or a Berezinski-Kosterlitz-Thouless transition as we go from a thick shell to a thin shell? And also, as we go to bigger and bigger and bigger bubbles, like what happens if we were to make multi-millimeter, or even centimeter size quantum gas bubbles? How does our intuition about BEC physics and superfluid physics on shells scale to those levels? Beyond these fundamental questions, this is also an experimental physics playground of sorts. So we can look at what happens as we inflate these shells, how fast, trying to study how fast we have to go or how slow we have to go. What happens if you inflate them too fast? How can we excite collective modes, perhaps, of shell BECs? And if you release these things from their bubble confinement, you can, in principle, see self-interference behavior. And so that's another avenue we're looking to explore, as to how these shell-trapped condensates, if we could make them, would interfere with each other. And along the way, there's a lot of experimental physics, I guess I would call it engineering here, really figuring out how to do the radio frequency dressing tricks, which is the central experimental trick we use to make these, how to make that all work on a remote apparatus that's flying around the Earth many, many, many times a day. So very, very different from a typical apparatus that we would use in the lab. And on the right here, I just want to illustrate this typical conceptual scheme that we have, that we make some potential U of R here that allows atoms to live in a bubble or a shell. The temperature of the atoms and the number of atoms we have then informs the density distribution of atoms living in that shell. So we could make a typical gas, a typical BEC here, which I've cut away a slice through here. Think of it as just a blob, the way a usual BEC is, a lump of matter held in the middle of a vacuum chamber. But as we inflate it, we can go from a thick shell configuration, and then at bottom here to a thin shell configuration. And that's how I'm conceptually thinking of this. This idea has actually been around for quite some time. So go back more than 20 years. Barry Garraway and Zobe introduced this idea as for two-dimensional atom trapping in dressed potentials. And the idea was that in the presence of gravity, if you try to make one of these bubble BECs, it'll actually sag and fall down, and you'll form a almost contact lens or shallow bowl-shaped Bose-Einstein condensate. The gravitational potential tilt makes this essentially impossible to do on Earth, given realistic physical parameters. This has been observed in multiple groups and is actually an interesting way to pursue trying to find two-dimensional quantum gases. But we really want to go beyond that. We want to actually have that contact lens rise up and fill around and paint the whole surface of this ellipsoid. And to do that, we really need to go to a free fall environment. There are some heroic tricks you can try to play to cancel out gravity, but none of them have really panned out terrestrially yet. So for the moment, we really have to go to microgravity. So how do we actually do this? Well, you could drop and catch your trapped BEC machine. I'm showing some results from the literature here of people. This is the Bremen drop tower at left here. So you can hoist a BEC machine up in the air or in a vacuum chamber, drop it, do some physics, and catch it. You could put it on a ballistic flight airplane, or you could actually have a machine in your lab that repeatedly goes up and down, up and down, up and down. So these are terrestrial ways of doing it. You could also, as with the MAIAS mission, put your BEC mission in a sounding rocket and shoot it up and get maybe 6 minutes or so of microgravity. And this is a pretty exciting result from the MAIAS collaboration recently, where they were able to do this. But at the end of the day, I think one the motivations for Cal and BCal in the future is to actually do this in perpetuity, to actually have continuous data from a machine that's making condensates in free fall that goes on and on. So how to do that? Let's ask NASA and JPL. So this is a picture of the space station, and you can see an astronaut there. And if you zoom in there, there's a little sticker, Cal, Cold Atom Lab, and that's where this machine is. And again, I'm a user of it. I'm not a designer or a builder of it. I would refer you to the literature, and I'll show you the link in a second. But it's a remotely operated BEC machine in microgravity, and it's been on the ISS since 2018. So what does the Cal facility offer us as experimenters on Earth? There's other PIs or other investigators who are interested in very weak traps, very low temperatures. So the ultimate limits of adiabatic expansion, for example, for purposes of doing atom interferometry with long interaction times. I'm personally, for this experiment, interested in the elimination of just the local gravitational potential. And in our typical atomic physics units, the kinds that I think of day to day, it ends up being about 100 nanokelvin worth of energy every micron, which is really a killer if you try to do these experiments on Earth. There's some details of what this actually looks like, but if you want to learn more about this machine, it was actually on the cover of Nature a year ago, and a really fantastic article from the JPL people describing their apparatus. All right, so given that we have an orbital BEC machine, how can we actually make these bubbles or make bubble potentials that atoms want to fill in and form a condensate shaped bubble, or a bubble shaped condensate, pardon me. And to do this, we're going to use I guess an old atomic physics friend in a new way, this idea of radio frequency coupling of Zeeman split spin states. And this is a little maybe in the weeds for a fundamental physics meeting like Marcel Grossman. So if you want to learn more about the techniques, it's in an article that we put together summarizing our idea there. So broadly stated, to see how we do this, the first thing you need to have is a space station with a BEC machine, and we do have that, thank you, NASA and JPL. And then we make a BEC, and the conceit here in this slide is that we have space at the bottom, and you can see the Earth and the aurora there, and then there's the wall of the space station in gray there. And we have an atom chip which traps which is our atom trap where our BECs are formed. And so the typical way we form these is to make a very, very tight trap with a almost needle-shaped Bose-Einstein condensate very close to the trap. And that's not useful for these bubble systems, just given the high aspect ratio. So our first step with this work is to expand it away and transport the cold cloud away from the surface of the atom chip, making something that's maybe more shaped like, I don't know, a rugby ball or an American football. When you actually do this, when you transport this condensate away from the chip, it actually shakes it and starts to make it oscillate and slosh around like a bowl full of Jello or a bowl full of jam. And that's no good. So we need to slow it down, and we do some very careful expansion protocols to try to get it to be still. So by looking at the resulting sloshing of the condensate, and this is the sine wave you see here, the sinusoidal data, if we expand over a slower and slower path, so an expansion ramp time of 100 to 200 to 300 to 400 milliseconds, the resulting sloshing or oscillation amplitude gets smaller and smaller and smaller, and eventually is lower than the limit of our imaging capability. The nice side effect of doing sloshing experiments like this is that it actually provides us a nice parameter to understand the properties of our trap that we can test against a model. So we observe about 100 hertz sloshing, and our model of this atom chip predicts within about 1% of that, which is where we're pretty happy with that level of agreement here. I'll move on from here. So can we actually make condensates in space? And the answer is yes, the Cal machine does make condensates. So we typically make about maybe 30 to 50% condensate fraction clouds with about 30,000 to 50,000 atoms. The critical temperature of these clouds is about 100 nanokelvin in our trap. It was maybe a microkelvin in the original trap, but we've expanded it. So these are already quite cold, but typical for BEC experiments. What you see here in these two images is a short time of flight dense cloud at the left, and we've released it into time of flight for 22 milliseconds. And on Earth, this cloud would have fallen down out of your screen long ago in this, but when in microgravity, it just keeps on sitting there. And that's one of the really fantastic things about this apparatus. Our imaging system is destructive, so whenever we take a picture of one of these runs, the condensate goes away and we need to make another one. The experimental cycle is about 1 per minute, and we typically get about 100 shots a day when we're running our main, when I have a data day as a user. Given the creation of this initial condensate, the next duty is to try to inflate this and transform the potential from a harmonic trapping potential into a bubble or shell-shaped potential. So when we do that, we see, first of all, that something happens, but it's going to take a little interpretive work to get through explaining what we see. So as we vary the radius of our bubble potential, so starting in upper left, we see a regular condensate. This number, 8 kilohertz, 16 kilohertz, 20 kilohertz, that parameterizes the radius of the bubble potential. So you start to see a structure emerge as this gets to larger and larger and larger radius. And it begins to look, one of my students said it looked like an old Star Trek Klingon warship, which I think is pretty evocative. I think of it as some kind of bird of prey, wings coming out like that. So something is happening there, but it's not particularly clear that it looks like a bubble yet. And I think we're going to have to link up to our model and help us understand what's going on here, because the way we're taking data here is actually as a column density. This is a shadow image taken of a bubble. And if the bubble is elliptical or slightly distorted, it's going to require a little interpretation. But regardless, there's the green line that I've put on that last image, which is meant to guide the eye. So to learn more about this, a typical trick in cold atom experiments is to just start with a hotter gas, and that'll give you a lot more atoms and a lot more signal to noise in your pictures to see what you can see. So we go to much hotter atoms and we start seeing what actually looks like a slightly biased bubble structure. So I'm going to draw, you might not be able to see my mouse, but I can envision a bubble structure all the way around, and it looks like it has some lobes on the left and the right. And when we're hotter versus colder, it fills in a little bit differently, but it definitely looks a little bit biased toward the lower side of your screen. Now, if we were in gravity, this would be much, much, much stronger. So the key ratio here is KT over mg, which gives a length scale for the pinning of a thermal system to gravity. And that would be about a couple microns on Earth here. So looking at the length scale here of about 100 microns shows that we are filling this up, this potential up. These atoms are not constrained by gravitational sag. So how to interpret this, we really need to look to a model and try to see if we can link up with a prediction here. So the way we think about this is just beginning with an understanding of the atom chip, calculating these dress potentials, and then either calculating a Schrödinger ground state or a thermal density distribution to see what would actually happen in these potentials. So at right, you see the results of the modeling of this column density. And one interesting result here is that as I applied different, what I mean by blur 1 and blur 2 there, these are different models of the imaging system, of the point spread function of the imaging system, is that if we actually have a shell distributed system and we take a column density of it, but it's elliptical, you actually see these poles or lobes appear at left and right that are a little bit of distortions from reality. They're caused somewhat by the imaging system. And we need to have to really understand this, we need to have a realistic, almost physical optics model of the Cal absorption imaging system. A lot of the initial reaction when you see this is that it doesn't necessarily look, I guess, like a bubble that you would imagine, your child playing with blowing bubbles in the backyard or something. But this is, again, this is a column density image. It's integrated along the line of sight. So if we look at our model and we take slices through it, it really does confirm that it is bubble-like, but it is in a distorted shape that when you look at it as a shadow image, it can be a little confusing. But it's nice to see the model slices look very bubble-like. And just as a reminder, to justify this whole affair, what's the point of being on the ISS? If I plug in maybe even just 1% of gravity into the model, we don't see anything like these structures. We just see a pinned, flat, sagged shell, sort of like the contact lens gas that we showed at the very beginning. We can try to go bigger and try to get these out to millimeter or even further length scales. And we've actually seen up to millimeter size or 2 millimeter size on the right there, length scales. The inhomogeneities become more dominant at larger length scales. And we also need to have significantly more atoms because they get spread out over a larger shell and become difficult to see. We can dynamically adjust the inflation. It's how we grow it, but it suggests that we should take a movie. And indeed, we can take a movie and I'll let that play a few times. So this is, each frame of this represents a different iteration of the experiment. And this shows an inflation of the shell up to about 1 millimeter size. And again, if we attempted this on Earth, all we would see is a progressively flatter and flatter and flatter disk pinned to one side of the bubble. And I'm getting close to the end of my time here, but I want to conclude with some of the actual physics we've been able to extract from this so far. So if we look at the thermodynamics of these shell potentials, we can understand it just by thinking of this as an adiabatic expansion. So as we start off with some entropy per particle in a condensate, and as we distort the potential, we should keep a final entropy, and we should be able to figure out what the new temperature is. And the intuition here is that you are squeezing the condensate into a shell surface, which implies some sort of adiabatic compression, but you're also spreading it out over a full surface. And it turns out that spreading out is actually winning, and you should see this as an effective adiabatic expansion. You can look at a couple parameters like the entropy per unit particle or per particle at TC, or more intuitively, perhaps looking at temperature versus TC. And this is modeling result on the right. So at left here, what we see here is variation of the temperature of the cloud as we increase its radius. So we start out with a partial BEC, so T over T critical maybe 0.9. So at the upper left of this temperature graph, this represents a very barely condensed condensate. As we expand, due to the change in the density of states of this potential, the gas is actually driven into a normal phase for a while, even though we're adiabatic, but phase space density changes. And eventually at larger radius, it returns to being condensed again. We haven't seen that yet because we actually haven't managed to be adiabatic. So when we do this, these are the key thermometry results in gold and the theory predictions or our model predictions in gray. If we start out with a hot gas around 500 nanokelvin and we inflate a shell, we see adiabatic expansion effectively, and we see cooling in the shell. And that matches up with our model pretty well. But when we try this with colder and colder clouds, we actually don't see the cooling that we quite expect. It seems to have a floor around 100 nanokelvin, or on right, maybe around 50 nanokelvin. And we think that that's actually perhaps due to bad thermometry, but more likely it's due to the non-adiabaticity of our expansion, that there's some, we're doing this a little too violently, and we need to be a little more careful with how we expand. All right, so where are we at here? We've made structures using Cal that are distinctly unlike their terrestrial equivalents. We've been able to make shell structures, ultra cold shell structures that are mostly painted over the surface of an ellipsoid-like surface. We have a pretty good model and intuition for the observed patterns we're seeing. Where we want to go with this, there's currently an upgrade for the machine right now that we're running. We really want to run with better condensate fraction to actually be able to see a condensate in a shell rather than just an ultra cold gas in a shell or bubble. There's going to be a new RF loop and a new chip upgrade that's we're working with right now, and that should have some better inhomogeneity. There's a few other ideas where we're looking ahead. There's been a sort of miniature explosion of theory ideas in this area, which has been really helpful, really fantastic to see the interest from the theory community as to what we can do with these, especially guided by Andrea Tononi and Luka Selaznic at Padova. And very raw recent data, this is sort of hot off the presses, with our the new Cal atom chip, we can actually see slightly better aspect ratios and maybe a little more uniform filling of this shell, but still some strange inhomogeneities that we're trying to figure out. But I'm particularly excited by the more circular or more spherical aspect ratios of this generation. So we're currently trying to write up the results that you saw in the middle of this talk. You should expect to see those out on the archive probably within a month or so. There's already a theory paper out on the archive on the thermometry. Dave Aveline at JPL helped build this machine. He's our co-investigator and is absolutely invaluable for understanding how to work the machine. And my theory collaborators at Smith College, UMass Amherst, and Illinois are listed there as well. And I think that's a pretty good spot for me to stop. Thank you very much.
Yeah, thank you very much, Nathan, for this really interesting talk about some fundamental physics. Are there any questions from the audience? Please, before, just unmute yourself and go ahead.
Maybe I can ask a question. Are you planning to continue your work on the BCAL instrument?
I would love to.
Okay, sounds good.
The BCAL instrument is should be capable of doing this kind of physics. One of the really neat things about the shells, this RF dressing technique, is that it somewhat comes for free with the tools or the hardware that are already on these BEC machines already. So it's not like a specific additional hardware ask. Additionally, there's a second technique that's being developed out of Ulm and Hamburg, I believe, to make these shells in a slightly different way. And it's we should be able to have a couple different techniques to propose to make shell systems with on BCal. So no, I'm certainly excited to try it. And on the cow follow-on experiment, which I think is going up next year, or being installed perhaps maybe next year or the year after, and then certainly on BCal as well.
Mm-hmm. Okay.
There's a there's an excess of ideas now from the theory side. We're getting quite behind. We're getting quite behind.
Yeah, and just a notion, I guess you will have to wait a bit longer than 2024 for BCal to launch. So maybe another question from the audience. Okay, if that's not the case, I would have one or two questions. You said that the experimental cycle is limited to 1 per minute. What exactly does limit this? And maybe just also the second question, with this limited cycle, how did you optimize the transportation away from the chip?
So my understanding of that is that the machine is capable of going faster, but not in a sustained way, that the atom chip heats up. So they've picked an average cycle time that can be sustainable to run throughout the whole day. And I think that's just a property of the atom chip machine that's at the core of it. I think if you needed to make them much faster, you could, but you wouldn't be able to do it very many times before the machine started to heat up. The optimization was not done in a particularly fancy way. We initially tried, and here maybe I'll go back to the graphic. There we go. Initially, we tried just a simple linear ramp, you know, the sort of violent yanking it away from the chip, and just saw massive sloshing, and that just gave us a good calibration or starting point. We developed a waveform from the literature that I think from Cass Sackett's group at Virginia that just looked at sort of a mechanical adiabaticity, and it was this hyperbolic tangent shaped waveform. It was not a GPE optimized transportation the way like Nasser Golul and Nick Bigelow's group have been doing. It was a little bit less fancy than that because we weren't trying to get to super weak traps. At the end of the day, this is I think 100 Hertz trap. If for the atom interferometry groups that are trying to get to 10 Hertz traps or something like that, they have to be much more careful and even use things like shortcuts to adiabaticity, or sort of even trying some sort of machine learning of different pathways. This wasn't so fancy. It was really more picking a waveform from the literature and then going out to 400, 500 milliseconds, at which point we started to see just some effect. I think the machine didn't want us to run longer expansion paths than that. But it also didn't matter at that point since we were below our threshold for detection.
Yeah, sure. Okay, yeah, thank you again very much. And I would say that we move on to our next speaker, which is Klaus Lemmerzahl from ZAM. Could you start sharing your screen?
Yes.
Yeah, that looks good. Yeah, looks good. And Klaus is going to talk about, maybe in the near future, with a bit more direct practical impact, maybe about quantum key distribution from space, which is quite a hot topic at the moment. And since Klaus' background is in general relativity, he's going to talk about relativistic effects you have to keep track of in these for this to use this. So please go ahead, Klaus.
Okay, thank you very much for this nice introduction. I will give a short introduction, then talk about quantum key distribution, then on the relativistic effects, show some results, and then come to a summary and outlook. As you already told, quantum communication is some main technology for the future because it promises absolute safe communication, realized, for example, by a quantum cryptography. And the basis of that is are the fundamentals of quantum mechanics, the quantum measurement process, and the no cloning theorem. So there's nothing to avoid this. And of course, one always has to deal with noises in the communication and the noises in the channel. On the classical side, there's this noise, there's a Shannon noisy channel theorem for classical communication, where he described that even for noisy channels, if the compression rate is not too large, one can safely communicate. There's a quantum analog of this theorem by Schumacher, and he makes an estimate on the classical information capacity in this noisy channels, in this noisy quantum channels. And noise can, of course, be thermal noise, scattering in optical fibers or in the atmosphere, or can be frequency shifts. And then, of course, in general relativity comes in, and also special relativity. And this is an issue if you make long distance communication, because for long distance communication, we should go to space because on ground, the performance is not so good. So here's a comparison between the link efficiency, as they called it, the capability to transfer on a safe way information in a space and on Earth. So you see there are many orders of magnitudes in between, and this is from this Nature publication of the Chinese people who made this quantum communication space experiment a few years ago. And this is shown here. So as I told, on the ground, there's only the possibility to have a few hundred kilometers of quantum communication. And if you want to have really long distance communication, you have to go to space. And this has been performed the first time by the Chinese in 2017 with the Meteos and satellites shown here with the performance. And although the technology is not so such hugely complicated, but it has to work. Yeah? And it is really an active area. There are national calls, European calls. There's this NASA decadal survey, for example, on this deep quantum network and so on. So there are a lot of activities, and then of course one has to analyze these configurations. So quantum key distribution, I will make a few comments on that. So one can make discrete valued quantum key distribution or continuous value quantum key distribution. The discrete value is with entangled states, for example, entangled spin states. This is doable, of course, but it's not so technological preferable, because if you want to, because there are some advantages of the CV quantum key distribution. It's easily implemented by using standard technologies, which can you buy from the shelf. There's a large detection efficiency, because if you use homodyne or heterodyne detection, then you reach almost 100%, where for single photon detectors, you reach the limit at the order of 50%. You have higher repetition rates in the gigahertz, and here for single photons in the megahertz regime. And it also has been demonstrated recently that there are higher key rates for the same decibel rate here for the same distance in the comparison between continuous variable and a discrete variable quantum key distribution. A good way to describe continuous values key distribution is a covariance matrix formulation. In formalism, we are doing that, but only very little, and this formulation is also very well suited to include GR effects, that is redshift and so on. There are many protocols to describe quantum key distribution in a continuous values regime. We are just taking the most basic one because we are doing here the proof of principle. We do a one-way reconciliation formalism and restrict to collective attack strategies. And we also need a local oscillator, and this then is one of the issues which is important for us. So you need the local oscillator in order to measure frequencies. And if the sender has an oscillator and the receiver has an oscillator, then usually it is done, or one can do it that the sender sends the local oscillator through the same channel to the receiver, but then this is not a quantum effect here, so this is open to manipulation. So the alternative is to have a local oscillator locally at the receiver, but then you may have the disadvantage of a mode mismatch. And this, of course, needs modeling of the mode mismatch, and of course, then again relativity comes in. This is the main scheme. You have the sender and the receiver. You have the channel, and with the noise photons here, thermal photons. You have the local oscillator here. You have the local oscillator here. And this then is the capacity of the channel then is related to the overlap between these two local oscillators. So we will come to that. So this is just the first setup what we are describing. Then we have the choice that we have coherent state or squeeze state, homodyne or heterodyne detection, or we have direct reconciliation or reverse reconciliation. We are usually taking here squeeze state. We can choose any one of these and reverse conciliations. There is a basic theory on what is the performance of such quantum communication, and there's a so-called blob bound. I've forgotten to give the reference. These are 3 authors. This has been published in Nature, I think in 2016 or so. And this gives a principal upper bound on the performance of quantum communication. And here, this is quantum communication for point-to-point communication from Alice to a Bob. And this is given by this quantity here. Tau is the transmittance, that is, so to say, the capacity of the channel. N bar is the mean photon number describing the thermal noise. And H of this is resembles the binary entropy and has something to do with it. And this, so to say, quantifies the maximum numbers of bits per pulse, which Alice can send to Bob. We are describing the quantum state sent around by this covariance matrix. V is the squeezing parameter for our squeezed state. Tau is the transmittance, and W is the noise. And the noise and the thermal average number and the average number of thermal photons is related by that. So we can now describe for homodyne detection and for heterodyne detection the maximum key rates. If you have here an ideal transmittance between Alice and Bob, and then it's just given by the squeezing parameter. And if we assume that the squeezing is of the order 10 to 5, this is, so to say, here the numbers for state of the art and the repetition rate of megahertz, then we get a key reference rate, so which is, so to say, the optimum of 83 megahertz. And now we are using this as reference, and now we are analyzing the tau, and the tau is then influenced by relativistic, by losses in the channel, as it has been introduced here, and in particular can be modified by the losses through a relativistic mismatch of the frequencies between Alice and Bob. And this is what we are going to describe now. So we are describing the photons by scalars. This is a simplified description. We are not dealing with the polarization. This also can be included, but it will be too complicated. We are assuming a killing vector that we have conserved energy. Then we get two equations for the for positive and negative energies. We can describe now the equation and annihilation operators of photons in terms of this basis, of this frequency basis, in terms of this decomposition here, like as it is a standard quantum field theory with the usual commutation relations. Since the gravitational, the electromagnetic fields, the photon itself carries no charge, both can be identified, and we have a decomposition of then we can describe a creation operator of the photon, which is created from plane waves or from energy waves of a finite bandwidth. Yeah? So we have a bandwidth f, and this bandwidth then gives an effective photon here. And photons, the commutation relation between two photons is given here because they may have different bandwidths here. We can now decompose this or describes or relates this to a certain observer, K. K is Alice or Bob, and then the formula looks like this here. And if Alice measures something, then Alice also knows what is which energies are contained in her measurement, and the same for Bob. One can derive such kind of commutation relation for the operators. We also know what the redshift is. The redshift is the frequency comparison. The redshift is a Z, so this is the frequency comparison of the frequencies measured by Alice and Bob. And since the photons should not disappear, then we can set up a relation between the bandwidth of Bob and the bandwidth of Alice. And this then gives the influence of this redshift on the performance of this quantum communication scheme. We not only are discussing the gravitational influence, but also the influence of the bandwidth. So there are various ways to describe beams. So we have usually it's taken the Gaussian beam. This is described here. There are also semiconductor nano laser diodes beams, which has a Lorentzian shape shown here, or the double-sided Lorentzian shape, which comes from a cavity-assisted parametric down-converting photon sources, and then the bandwidth is shown by this formula. And this chi is here related to the conversion efficiency of the down conversion process, but this is not so important for us. So we are also discussing various shapes of the laser beam. The value or the performance of the communication is characterized by the fidelity. So this the fidelity between of the two density matrices is given by this somehow strange expression here. So this is the trace of the square root of the product of the density matrix, where again the square root is put in. Amazingly, this is symmetric between the two density matrices, and so it is. This is derived from some general principles, and this is the meaning. The meaning is, so to say, the overlap between these two density matrices. Okay, now we have these. Our density matrices are now matrices, so these are quantum states given by quantum states. The quantum states are given by these creation operators for Alice and Bob, and this is so to say given by this delta squared, and delta is just the overlap of the bandwidth at Alice and at Bob, and of course there then this gravitational redshift comes in, and if you calculate that then this delta for the Gaussian beam turns out like this. From the semiconductor, the Lorentzian, and the double-sided Lorentzian comes here. And you see the Z comes here. It comes in here in a different way. And the characteristic feature here, the experimental characteristic feature, is the R. And the R is, so to say, the peak frequency over the frequency bandwidth. And if we calculate that, if you make an approximation for small redshift, then you see that there are really different results here. That means that indeed various formulas for the composition of the laser beam give different performance of the quantum communication. Indeed, if you have a certain type of lasers, and so then we should not take the Gaussian profile, and indeed you will see that compared with the Gaussian profile, we get some really significant differences. One also can discuss the redshift is of the order 10⁻⁴ to 10⁻⁶ in the vicinity of the Earth, and in the standard experimental physics, one has this R, which is the peak frequency over the bandwidth, can be of the order 10 to 11. So, and you see that mainly the R times Z is here important. So at least in the at first order, the R times Z is important, so that the combination of R with Z then may become large. So the secret key rates and the block bound really may differ by orders of magnitude for different frequency profiles. Here are our first plot. So this is a block bound, and these are in a two ways to plot this. So we have the Gaussian profile is given by this plot styles here. The solid line is Gauss, dashed is Lorentzian, dotted is this PDC profile, and the colors are related to the values of R, and they are shown here in this inlay. And if you have first here's the logarithmic plot, the one side logarithmic plot, you see here that in the general relativistic regime you will see some differences, special relativistic regime also, and but here one has no access or graphical access to these values here. If you have double logarithmic plots, then you can explode here a bit the small regime. And you see there are really differences between these various R values and these profile functions. Yeah? So this is really different for different sets. And here, this is our Z regime is 10 to minus 10 or a bit better. Yeah? So here, and then you see that there might be some severe influences of the profile on the related to gravity on the performance of quantum communication. Yeah, I'm going a bit. Yes, one can here's just really plotted the Z times R term here, also in the first plot. So in here single logarithmic plot and the double logarithmic plot, and you see again here in this way the importance of the Z times R. So since R is large, Z may have some influence here. So Z is of the order 10 to minus 6 to 10 to minus 10. Here are some results. So the plots have been done by Roy, and so here the blue is a redshift. This is the usual redshift of a satellite in the equatorial plane if it's orbiting the Earth, and the Alice is sitting on the ground, also in the equatorial plane, and then you here see the key rates, which are here are the orders 10 to minus 10, 10 to minus 20. So there are differences in the key rates. Here we have again an equatorial geostation and an equatorial satellite, but analyzing this for a different height. Then you see that for geosynchronous orbits, the key rate is the best. This is now highlighted here. This part and yeah, just the redshift and the key rate again for this various R terms and for the R terms and for these profiles. The same here.
Klaus, I'm going to give you 2 more minutes.
Okay, okay. Here we discuss the inclination of the satellite, and here also if the satellite is really moving, then the time dependence, which is so to say related to the azimuthal angle, we see here really influence of the relativistic effect. And also we discussed satellite to satellite communication for two satellites on circular orbits, and the best performance is if the 2 satellites have the same orbit. Also for orbits which are inclined to 90 degrees, so or with various degrees, and you see here also some influence. Okay, so we are just in the course of discussing various constellations. Okay, so that is what I wanted to show. So there's an influence of relativity on key rates if you are discussing quantum key distribution from space. It definitely depends on the laser beam model, and there's this influence of the gravitational redshift, and there are certain constellations where the effects are crucial and should be avoided. In many cases, it can be absorbed through some numerical adjustment. As outlook, one should of course optimize the link, so the result of this can be used for practical purposes. Also for optimizing the links within satellite networks, And maybe if one is in the crucial cases, we may use these crucial cases for new experimental tests of general relativity. Perhaps these effects are then enhanced through this particular configuration and the setting of parameters. And perhaps we can now, in a few years, we can then, as we do it with the GPS, that each day there will be millions of tests of the coupling of quantum mechanics to general relativity. So thank you very much.
Yeah, thank you very much, Klaus, for this really interesting talk about, as I said, quite a hot topic. So are there any questions from the audience? As always, just unmute yourself and go ahead.
Maybe a question.
Yeah, okay.
I know Klaus is really always on the ideal, let's say, view of the things, but I'm more from the, coming from the engineering side, maybe. So I would like to ask you, what do you think is the timescale to be able to detect these relativistic effects really, or to handle these effects? Because I think the more disturbing effects on board of a satellite are really shadowing these effects, or am I wrong from that point of view?
If you have satellites to satellite communication, then it's just the instrumental effects, that is that you have a good pointing, or that the receiver is working, and so on. Because in vacuum there is practically no effect on the communication process. And but if you have communication between Earth and satellites, then you have to take into account the atmosphere, and this then is this may give some, or may also give, or certainly give some effects, and there are some studies already made with the generic atmospheric models by Dagmar Bruss from Düsseldorf, and there she has shown that in the night it is better than on day, and the humidity plays a role, and that and this leads to the fact that the satellite has to be really up and not at a large angle. Yeah, so this could be, this already has been discussed. Yeah.
Mm-hmm.
But relativistic effects also has been discussed earlier by Fuentes, Bruschi, and other colleagues, but they always restricted to the Gaussian profile, and also made some other and always restricted to a circular orbits and radial communication. Yeah, so they did not make the full variability of the connecting laser beam.
Thank you.
Any other questions? If not, then maybe I would have I guess, a more conceptual question regarding the quantum key distribution. I know that, of course, if with quantum cryptography, man-in-the-middle attacks are outruled. But how does Alice know for sure that Bob is Bob and the other way around? So.
What was the question?
How does Alice actually know that Bob is Bob? Because for that they need another communication channel, which is secure.
This I cannot answer. So I'm not so much an expert in that, at least now. Yeah, I'm sorry, I cannot answer that. Yeah.
Yeah, no problem. It's just something that came to mind.
Yeah.
Yeah, okay. Then I think I would hand over to Michael again to announce our last speaker.
Yes, thank you. Yeah, so I would like to ask, I hope I pronounce it the correct way, Xingfeng Zhang, is it correctly?
Yes.
To share his screen. Yeah, thank you. It's working. We can hear you. We can see you.
Okay.
Yes,
Thanks.
and our last speaker today is Mr. Zhang from China. And he's going to talk about orbit and constellation design for Tianqin. I hope I pronounce it the correct way. I'm really not sure.
Close enough.
And okay, and he's going to give us a progress review of the mission. Okay, please, it's your stage.
Okay, thanks. First, thanks to the organizers. So I will talk about some of the recent progress we made on the orbit and constellation design for Tianqin. And this is a joint collaboration with my students and colleagues at the Tianqin Research Center. Can you hear me?
Yes, yes, we hear you.
I think my screen is freezed. It's not responding to my keyboard.
Oh, maybe you so you can you go off the presentation mode? Can you go out of this mode?
No, I cannot.
Okay, no problem. So maybe.
Screen.
Okay, then no problem. Maybe you can shut down your computer and log in again after some. We
yes,
wait for you.
Please, okay, please give me like 3 minutes. I think.
Yes, sure. We wait for you.
Thanks.
Yes.
Jesus.
That can happen. It's no problem. Okay. All others are still there. I'm not sure if we all are shut down now. Hauke?
Here.
No.
Okay.
Good.
Yeah. I just have to leave, unfortunately, at 12. But for now, I'm still here.
Okay, that's fine. Yeah, I hope we can get him. I still see him in the list, so
Yeah,
I don't know if I have to do something. And still maybe I can we do something to kick him off? And maybe that's easier to log in again. Now he's yeah. Yeah, that's always a problem then. I'm sorry for that. So maybe we could, I ask a question for Klaus again. This is something which came up to my mind just now. So do you think it's worth to go for a complete simulation, which means that you try to optimize the network with a satellite constellation, with a complete orbit propagation and system modeling, including all disturbance effects coming from the system to the sensors and receivers, and as well try to build up the relativistic modeling with the signals? Do you think that's handleable? So I think that's something which comes to my mind, that is quite a huge simulation. Do you think we could handle this together in some way?
So yes, I think this should be done, yeah, in order to optimize the system. Yes. Mm-hmm.
Okay, then maybe we should talk about that maybe the next days. That would be a good approach. Okay, thank you. Okay, I see now our speaker is back again in the meeting, and I see the second slide, I think.
Okay, yeah, sorry for the delay.
No problem. We just waited for you. That's fine. Yeah, please start.
Okay, second page. So here's the outline. So basically, we will discuss 4 papers we just recently published on the subjects. Here are the archive numbers. So the first, for those of you who aren't familiar with the Tianqing, so the mission is to deploy a 3 drag-free control satellites in a circular high Earth orbits with a 100,000 kilometer radius, and they form a nearly equilateral triangle constellation with a arm length of 170,000 kilometers. So the satellites exchange laser links to detect gravitational waves in the millihertz frequency band. And since it's in a high Earth orbit, so the constellation plane is nearly fixed and set to be almost vertical to the ecliptics. And the normal vector is pointing at a reference source, J000806. And so Tianqing features a geocentric concept. So it is facing the challenge of designing and utilizing high Earth orbits to achieve the best effect. So being close to the Earth has certain benefits. To name a few, such as a lower launch cost, a shorter transfer duration, and easier data communication, etc. But there are also concerns. So is the constellation stable enough in a Earth orbit? So how to choose the orbit? And what about the Earth and the Moon's gravity disturbance to the intersatellite science measurements? And also how to handle the eclipses due to the Moon and the Earth. So we will try to shed some light on these issues. So the first topics on the constellation stability optimization. So the motivation here is that under gravitational perturbations and also the initial orbit errors, so the constellation can slowly drift away from the nominal equilateral triangle. So there are 3 performance indices: the arm length variations and the relative velocities along the line of sight between 2 satellites, and also the breathing angle variations. And here are the requirements on these indices. And the most critical one being the breathing angles, and allowing for like plus minus 0.1 degrees for the first 2 years. So the constellation stability is crucial to the mission and affects several aspects of the science payload design. So to alleviate pressures on instrumentations, so it would be desirable to find orbits with deviations from the equilateral triangle as small as possible. So that is our goal. In orbit simulations, we use the pure gravity orbits, and they are calculated by the GMAT software. So in this case, the orbital evolution is determined by the initial conditions alone. So we just need to adjust the initial orbital parameters. There are 18 of them to stabilize the constellation and meet the requirement. So it is a 2-step optimization. So the first is to set the semi-major axis and the mean orbital planes of 3 satellites equal by iterative relations. And then next, to minimize the cost function that encodes the stability performance by a numerical search over the orbital parameter space. So here's what the cost function look like. So here are the results. The plot shows the time evolution of the relative velocities between satellites on the left, and also the breathing angle on the right. So the constellation can be stabilized to the level of plus minus 0.1% in the arm length and 4 meters per second in relative velocities, and 0.1 degrees in the breathing angles, at least for 2 years. And the detector pointing can be made quite stable, and they vary only by less than 3 degrees in 5 years. Additionally, we have also identified stabilized orbits with 6 other detector pointing along the lunar orbital planes. They can be used as future backups. Okay, so next topics on the orbit selection. So the preliminary design for Tianqing has assumed a 100,000 kilometer radius and facing the J0006. But it begs the question, so what about other orientations and radii? And can the stability be further improved? So it should be pointed out that the nominal orbit design for Tianqing should take into account and trade off between a variety of factors. Here, we will just focus on the impact of orbit selections on the constellation stability to see how this stability is affected by different choices of orbits, and also to identify permitted parameter ranges for a refined and more comprehensive future orbit design. Okay, so we will carry out a single variable studies and a large-scale parameter search. So the parameter ranges are inclination from 0 to 180 degrees and ascending nodes taking on 4 values 90 degrees apart, and also the radii from 60,000 kilometers to 150,000 kilometers. They are given in a Earth-centered ecliptic coordinate system. So the previous optimization method was pretty slow, so we proposed a more efficient algorithms that dispenses with a slow blind search of the cost function minimum in the 18 parameter space. So again, the first step is to set the mean semi-major axis and the mean orbital planes equal for the 3 satellites, and also set the mean phase separation between satellites to be 120 degrees. So the second step is to include the initial times at independent variables in the optimization, and this can reduce the eccentricity growth of the orbit. So the entire algorithm is now deterministic, and the runtime has been reduced from several days to 2 hours. Now here are the results. So the plot shows the dependent.
Hello? We can't hear you anymore. So at least I can't hear you.
No, I can't either.
Still not. It was perfect before, but now, unfortunately. Okay. No, we can't hear you. I don't know what changed. We see your slides still. Nothing to hear. I'm sorry. That's a pity, because I like that idea of this talk, but I'm not sure. I think maybe there are some technical problems coming up again and again. Maybe you can try to log in again. I'm not sure if that helps. I can't do something about. We hear you sometimes a little bit, just like a part of a word, but that's it. I don't know. I think there are some technical problems which we can't cover at the moment, unfortunately. I think maybe I don't know, Hauke, what do you think?
Yeah.
What should we do?
Could you maybe just try logging out of Zoom and logging in again?
Yeah,
that would be maybe, I guess, the best thing.
Okay.
I know that some people are.
Now we hear you.
You do? Okay.
Yes. Perfect.
Yeah, you're
okay.
back.
It's a miracle. Okay. I guess I will continue So can you see the slides?
Yes.
Okay, good. So where were we? Yes, the plots. In general, the retrograde orbits perform better than the prograde orbits, and the constellation can be made more stable with a inclination roughly 90 degrees and 140 degrees. And also ordering the longitudes of ascending nodes omega has only a small impact on the stability, allowing it the freedom to reorient the detector. The stability tends to degrade as the radian increases. And in order to keep the breathing angle within 0.2 degrees, the radian should not exceed 113,000 kilometers. And also we have to avoid the orbital resonance with the moon, where the peak shows up on the plot. So overall, the selectable ranges are rather broad for Tianqin and permitting a future adjustment. Okay, next topics on the Earth and the Moon's gravity disturbances. So we have already seen that on a large scale, the gravitational perturbation can change the arm length and the breathing angles. And on a small scale, so the perturbation directly impinge on the task mass's geodesic motion, and it may enter the detection band and induce what we call a orbital noise. So this is similar in nature to the Newtonian noise in the ground-based detectors, such as LIGO, Virgo. So we need to assess the quietness of the ambient gravity field environment for Tianqin, particularly in the detection band. So for this purpose, we choose the range accelerations as our observables, so which is just a second time derivative of the separation between two task masses. So the criteria is first to compute the amplitude spectrum densities of the range accelerations and compare it with the residual acceleration noise requirement between two task masses, which is just square root 2 times 10 to the minus 15 meters per second square per root hertz. Okay, again, we use pure gravity orbits, but this time they are propagated in quadruple precisions by our own code. So this is to overcome the insufficiencies of double precisions. And the detailed force models include the solar system ephemeris DE430, and also Earth's precision nutation models IAU 2006, and also the Earth's static gravity field EGM 2008 up to a 12th order and degree. Also, the Earth's tides follows the RERS Convention 2010. Yeah, and additionally, we added the moon's and the sun's non-spherical gravity field. So here's the results. So we can see from this plot that the Earth and the moon's gravity field is dominating at the lower frequencies, and they fall off very quickly at the 1 times 10 to the minus 4 hertz, and it does not enter our detection band. So for a comparison, the fall off frequency for Grace follow-on is at the 4 times 10 to the minus 2 hertz, and that's because Grace follow-on is in a low Earth orbit. So this means that a 100,000 kilometer radius should be high enough already to push these disturbances out of the frequency band. So we were quite pleased with this result. So here's a breakdown of the total effect, where we can see that the effect is dominated by the moon's point mass below 4 times 10 to the minus 5 hertz, and above that by the Earth's static gravity field. And everything else are well below these two main factors. Okay, the last topics on eclipse avoidance. And we know that entering the shadows can cause the thermal shock to the science craft and also disrupt the steady power supply from the solar rays. So both of which can generate the payload performance. So the issue has been considered a major risk for geocentric missions in a NASA report, and the remedies had not been well studied. So in fact, the most straightforward way or effective way to overcome this issue is to come up with an eclipse-free orbit design. So this is to require that the satellites shall undergo no eclipses during the 3+3 months or even longer observation windows within the 5-year mission lifetime. It should be pointed out that the Earth eclipses are unavoidable, but they only occur well outside these observation windows, hence they are less worrisome. So there are lessons to be learned from previous missions like Herschel, Planck, even James Webb Space Telescope, also Trichel for Chang'e 4 missions. They all have executed a certain eclipse avoidance in their orbit design. And also, we have at least 3 strategies. First being the avoidance maneuvers, which consume the propellant. That's not what we want. And the second, initial phase selection, also the orbit resizing. The last one means to adjust the phase rate of the satellite. So we will use a combination of these last 2 strategies for our design. So for Tianqing, we have proposed these 1 to 8 synodic or resonant orbits with respect to the moon. And it means that the satellites completing 8 revolutions in 1 hour, in 1 lunar month. And the idea is to set the satellite motion in a repeated phase relation with the moon's shadow. So this is better visualized in a moon-centered coordinate systems. And that is correlating with the sun to moon vectors. So in this coordinate system, the moon's shadow is aligned with the positive axis. And if we draw the satellite's orbits in synodic resonance, you're going to see these repeated patterns in the trajectories. So in order to reduce the eclipses, all we have to do is just to align the moon's shadow cone with this one of these big gaps here. So that's the idea. So these resonant orbits corresponding to a orbital radius of 100,935 kilometers. And the permitted eclipse-free initial phase range is about 15 degrees, granting a big margin to the orbit control. So this plot shows the dependence of eclipse-free initial phase range on the orbital radius, where we can see a big sharp peaks here at the 100,935 kilometers here. So in contrast, for a non-synodic resonant orbits 100,000 kilometer radius, we have found no orbits that can meet the requirements. And in conclusion, so we are now able to avoid all eclipses in 3+3 months observation windows and fulfill the constellation stability requirements. And moreover, the eclipse-free observation windows can be further extended to 4+4 months and even longer at an acceptable expenses of reduced permitted initial phase range. Okay, here's to summarize. So for Tianqing, the expected level of constellation stability is about 0.1% in arm length, 4 meters per second in relative velocities, and 0.1 degrees in breathing angles. And a laser ranging station has been built in the Zhuhai campus, and it has the capabilities for a precise orbit determination at a centimeter levels. And it can help to realize these orbits. And also setting the orbital plane vertical and avoid orbital resonance with the moon can help stabilize the constellation. And also with a 100,000 kilometer radius, the Earth's moon's gravity disturbance fall off at the 10 to the -4 Hertz and present no showstopper to the mission. And last, the eclipse issues has been largely resolved for Tianqing, and there's no eclipse events during the observation windows with the proposed 100,935 kilometers radius. Okay, finally, here's a little advertisement for our centers. So we have a faculty and postdoc position available. Here's a picture of our research buildings and a picture of our ranging stations on top of those mountains behind. Okay, thanks for listening. I'm happy to answer questions.
Yeah, thank you very much.
Thanks.
It was an interesting talk and a bit exciting because of the technical problems. Yes, are there any questions from the audience? Just unmute yourself and ask the speaker if you have something you would like to know. I see there are no questions, I think, but I would like to ask you, I guess, two things.
Okay.
One thing is in your, it's just everything connected to the table you showed. I don't know which number of the slides where you compared. Yes, there was. I guess there was a table.
Oh, there was a table
with the
you mean the
disturbances
requirement?
and with the disturbances and things you considered for your. No, not this
okay.
one. I guess after that. Yes,
This
a little
one?
bit more. No, yes, this one. This one, yes. I would like to ask you two things. So one thing is you consider Sun's orientation and Sun's J2 term, but I think that's all connected to gravity. So do you consider in some way some kind of radiation effects like solar radiation pressure or something? Because it's not listed here, but I think for an Earth-centered orbit in some way, it's still something you should consider for even, especially when you want to go to drag-free. Do you consider
yes,
it in some way?
No, actually, but it's a valid point. I think we always assume a pure gravity orbit because the satellites are drag-free controlled, so we assume that all the radiation pressures has been shielded by the drag-free systems. So
okay, so you are already assuming an ideal, perfectly working drag-free control. Okay,
yes.
Okay.
For the simplicity of the problem.
Yes. Okay. Yeah, I see. But if you want to go to the more system, so to speak, system or subsystem simulation, you would like to include these. Yes.
Yes, you are right.
Maybe periodically varying effects. Yes. Okay. And another thing is you consider here atmospheric tides. I think, yes. But
yes.
if you go for such a high orbit, I'm wondering that you include these things, or do I get something wrong? So if you go for a 10,000 kilometer orbit, or is it not Earth atmospheric? What do you mean here?
Oh, I think here we just follow the RERS conventions. Oh no, I think it's not in the convention, but something extra. Yeah, I think it was. This is something recommended by the convention, I guess. Sorry, I can't remember clearly.
Yeah, because usually if you assume such a high orbit, yes, of course you can consider maybe some tides, but I was wondering if you include really a complete atmospheric model, because I think that's maybe a bit too much work to do. But this is just something what comes up to my mind when I had a look at this table. So yes, okay. Okay.
Yeah, we just try to be complete.
Yeah, sure.
Make sure that we don't miss anything.
Yes. Okay.
Okay.
Yeah, thank you. That were my questions, I think.
Thanks.
And maybe another question. What kind of accelerometer do you expect to be included? So do you have something specific in mind, or is it just test masses in some way located in a future satellite, and you are not all maybe I'm not really familiar with this mission, so I don't know. So there's no satellite design already in some way available, right?
There are some conceptual ideas on the satellite design, but also I think on the for the accelerometers, there has been a lot of development in the center. I think that there has been like 20 years accumulations of technology on that matters, and there has been like at least 3 flight tests of accelerometers. And the recent mission, Tianqing-1, you probably have not heard about it, and I think has already reached the the residual acceleration noise at about 10 to the minus 12 meters per second square per root hertz. So we are stepping towards the final goal here. So yeah.
Okay. Yeah, thank you very much.
Oh, yeah, thanks.
Are there more questions? This seems to be not the case. So yeah, some of the speakers already left due to other meetings, I guess, and maybe Nathan went back to bed again. I don't know. And I think yes, both Hauke and myself, we would like to thank the speakers who are still in the room for this interesting session and the contents which were presented. And we come back to you either by email or via the Massa Grossman interfaces or web pages or whatever is provided by them to ask for the proceedings. I think there will be a process installed. I don't know when this will take part, but I think we get back in contact and we will create a very nice chapter on this topic of fundamental physics in space. And yeah, Hauke, do you want to say something?
No, I just want to also thank all the speakers and, well, those who are still here. And yeah, it was a very interesting session, I guess. No, I think. So thank you again. And just, yeah, another, what's Hinweis in English? I can't remember.
Hint? Remember?
Yeah, information maybe. There will be a link sent around tomorrow from the organizers, where you can, if you like, watch the talks again. So maybe to to get the links to the interesting papers from there. And yeah, just an addition from my side. So
yeah. I think we thank you. And if there is nothing to mention anymore, then from your side, then yeah, I was really happy to see some of you again. Not all of you, but some of you really after a long time. I mean Manuel by that, of course, because we've been in contact for a long time and stopped that, I guess, at the beginning of Corona. So I was really happy to see you here. And Klaus, of course, and Mr. Zhang, and already the speakers who already left. I was really happy to have them here. And of course, I liked Hauke co-chairing this session. And yeah,
thank you.
Hopefully
Likewise.
hopefully see you next time at the Massa Grossman meeting. So, and okay.
Bye.
See you. Bye.
Yeah, have a nice day.
Ja. Dann halte ich mal an hier.